Hey, I'm Agastya. I'm a graduate student in computer science, and in this video, I'm going to reason through how a RAG system actually works by building one from scratch. Not as a tutorial, not as a polished demo, but more as a way to think through how these systems actually work when you break them down into first principles. For this video, I'm not trying to be clever or optimize anything. I just want a clean mental model that I can code. So before writing any code, let me quickly explain how I think about RAG at a systems level, and then we can build it piece by piece. So RAG is just retrieving the relevant information, can be in text or documents, and give it to an LLM to generate more accurate answers. To do this, we need to understand the documents and then create a meaningful representation of them. And once we have created a meaningful representation, we would be able to extract the relevant information from this and give it to the LLM. A RAG system has five components: document ingestion, basic reading a file, input output in Python. That is how I'm going to be implementing it. Document chunking, split these documents of text into small, consistent size strings. Why we do it? So that we can have a consistent group of text, and these groups of text can be the candidates which we can rank, and this is the information which we are essentially passing into the LLM. And common reasons for doing this, why it's done according to academia and industry, is because it enables parallel processing, it enables not having too much load on the GPU, better ranking, as I said. So let's first just build these two things. It's going to be very simple, a very simple Python file. Um, it is taking in a text file and separating this into chunks. So in this class, I want to give in a file path. That is how I'll give it the file. Chunk size. What is the chunk size? What is meant by chunk size? It is just the length of that list of words which we are going to divide this document into. You can also think of it as a sliding window. What is a chunk? Like a sliding window that goes over the document and just gets these. And for just this demo, I'm having it as 10. It's advised to keep it between 200 to 500. Also can be larger, smaller, depending on your machine, depending on which LLM you are using, what kind of context window it has. Overlap is just the overlap between two consecutive chunks. If a chunk size is 3 and overlap is 1, then the first chunk out of this, if it was all the text in the file, then the first chunk would be take in a, and the second chunk will start, because an overlap of 1 is there, then it will start here. This is done to have continuation in the file. Okay, and then def create chunks. So this function, this function is all we had to write in this file. Just read the file and create the overlapping chunks of text. Okay. This code looks correct. Yeah, we open the file as f, and f dot read. This gives the file as a long string. I'll just read. And this text, this is containing a very long string which is having all of the text from that file. And now I want to extract all the words from this text. And now let's get those chunks for I in range 0 to length of. So we go over this very long string and we step on this sliding window why I am writing this here. It is the step size. Why is it like that? Because you think you have a window size of 3 and then overlap of 1, then the second one will, the first one starts at 0, second one will start at 3 minus 1 is equal to 2. Chunk is equal to words. I to I using slicing, and then yeah. Okay, let's write a test case for it. I mean, just make let's make a sample file and okay, and give it create an ingestion object, create chunks, and print the chunks. Let me see. Cool. So because chunk size was 10 and this was a very long file, so yeah, we got 4 chunks out of this file. That was the first 2 steps of our rack system completed. Now embedding. Okay, so for the embedding part, we are using TF-IDF. What is TF-IDF? It is one way to say how important this text is or this bit of information is. In this case, information only consists of words. So there is a document contains a paragraph and it has some 100 words. How do we decide that this document is important or not? We see if this document contains unique words. And how do we mathematically model it? We just calculate for each word in that document. We see if it is unique or not, and we give it a score. And that score quantifies its uniqueness. And this is how the score is calculated. It has 2 things. Term frequency, it is the number of times that term appears in that document upon the total number of terms in that document. And then inverse document frequency, which is out of all the documents that are there, how many documents does this term occur in? So how unique this term is to this document, and then how unique this term is to all the documents. This is something for later. Let's implement this. Calculate the TF-IDF scores. This is the first thing we are doing. We are calculating this for each chunk in the set of chunks, right? So this put this text chunk, list dictionaries, list vectors representing TF-IDF scores for each chunk. class embedding. Wow. So term. So yeah, let's calculate TF-IDF first. So I'm going to calculate the term frequency. But even before that, I have to build a vocabulary. So uh, why building vocabulary is there? Because we cannot just go over all the words in the text and calculate their relevance, because word might be repeated. We need to first get all the unique words in the document, and then we will create a vector where uh, every single entry represent the uniqueness of every word in that document. Therefore, we are getting all the unique words in this document. Great. And now I have all of the words in this document. So why I returned this as a list is because I might need to change this vocabulary, add new things to it. And in a set, you can also add, it was just suggested here. Now I will calculate the term frequency. Uh, yeah. So first I have defined this vector of term frequency into, yeah, this is just initializing a very long list containing zeros, and these zeros will be filled by the TF scores first, and then we'll multiply them by the IDF scores. Words is equal. Yep, all the words for, so we iterate over all the words. If word are in the vocabulary, yes, and the index is equal to vocabulary dot index of that word. This just returns in that list at what index that word is, and we just add one to it. We are just storing the occurrences of this word in the list, and then yeah, and then we can just return TF vector upon length of words. So we got the term frequency here, and inverse log frequency. Yes. So IDF just has to be computed once. I'm using math for doing the logarithm. Okay, won't hurt. Now, the total number of words. Okay, yeah, this code looks correct. We are counting the number of documents in which this word appears. So, sum of 1 for chunk in self dot chunks if word in chunk dot split. And then we, for that word, we get its IDF score. Mhm. And we return the IDF vector. And then this is the simplest one. Uh, okay. And this IDF vector, TF-IDF vectors, and for chunk inside of chunks, TF vector and TF-IDF multiplication, and yeah, okay. Let me write test case. Cool. I know this part of the code was a little text heavy, but if you read the TF more about TF-IDF, it's very simple, and we are just doing a dot product of these two lists, essentially multiplying the corresponding elements of this list here, and that is the whole TF-IDF score of this but one chunk, and then we are doing it for all the chunks. So it should work. Mhm. Unsupported operand types. And which line? Line 25. Length of word. Wait. Okay. So yeah, I should handle division by zero. Now words count upon total words for count in TF vector. Okay, so I thought I could just divide every single element in that list by the length of the word. Um, but this is just for every uh, TF score. Let's make it more intuitive. Total words, TF vector. Nice. So I wrote these chunks and we got the TF-IDF vectors for these. Great. Which means that the embedding part is also complete. Now it's a very simple part, retrieval part. Great. So for the retrieval part, uh, when does this happen? When we get a query. So for this query, we get the similarity of this query for all of these chunks that we have embedded so far, and the chunks which have the most similarity from this query, we return them. And for calculating the similarity, we use cosine similarity, the cosine similarity, and uh, return the most similar documents, or documents, just chunks. Okay, So in this class, I want to give the query that the LLM has been given and all of the chunks. Okay, and that is it for now. And so here we have to create the embeddings of all of the chunks as well as of the query. So to do this, because our embedding.py, this just takes in chunks. And what is chunks? Chunks is chunks is a string. It's a list of strings. So we have to add our query string at the end of all of these chunks so that the very last vector which our embedding gives us, that the very last vector from that embedding will be the vectorization of that query as well. And one question might be here that why did we not separate the query into chunks as well? So chunking is for documents because documents are usually very long, but queries, they are they are not as long as documents, and the size of the query is usually comparable to the default size of chunks that we already set. Therefore, we don't have to do chunking on the query. So yeah, I'm not sure if my explanation was adequate, but um, from embedding, input embedding, self bedding embedding model. Yeah. So inside the embedding model, we have given all of the documents that we have, and we have given the query appended added. And why is it as a list? This is just to handle the types. It is a string, and these chunks, this is a list of strings. So we cannot just append a string. So we just to do list addition, we are doing this. We could have also done this as total chunks is equal to chunks dot append query, and then inside the embeddings pass the total chunks. Now, cosine similarity. Yes, and this takes two vectors. I think we are clear on what a vector means. We're going to use math for the for what exactly? Oh yeah, for the square root part. Dot dot and let's put this. Yeah, we know what dot product is. So we are in this implementation just going over these two lists and multiplying the corresponding elements and adding them. So multiplying these two elements for A and B in zip vec 1, vec 2. So for this to work, these vec 1 and vec 2 should have the same number of elements. Otherwise, zip function won't work. Magnitude of 1. And to calculate the magnitude of a vector, we have to just go every single element, get its square, and then keep on adding that. And what we get, this sum that we get, we take the square root of it. So that's what we're doing here. And again, I'm interested like how it would be if I write it in Python functions. Sum of hmm, map. Yeah, but this is just another way to write it other than less comprehension. Just wanted to see. And handling division by zero. Cool. Great. Now just the last main function. The retrieve. Nope, nope. Yeah, I think we can initial give one more. Yeah, top K. I just want to name it retrieve. So, and cool. So document vectors, we are going to be dot embedding model dot compute TF-IDF until the we are not including the last one, because the last one would be the query, the embedding of the query. So last embedding we are not including, and query vector is just going to be mhm, -1, and similarities. Wait. Hmm. Okay, so the similarity is will contain the list of tuples. Yeah, great. Every similarity and the chunk, so the chunk and its similarity value. So for every chunk and document vector. Great. So it has the name of the chunk. What? I've had this. Let me do this again. Similarities. Great. I think it's better to build an index here, because what the previous one was just listing down the chunk and the similarity score. I think it's better to just write that the index number of that chunk, like where it appears in this list of chunks, and next to it write the similarity score, because this indexing will help us in sorting them later onwards, and it's just better, more memory efficient. Document vector and okay, similarity is equal to self dot cosine similarity, query vector and document vector, and in similarities we just append this, and then we sort these similarities. Key is equal to lambda. Okay, and this key has to be a function. This function is x such that x1. So the at index 1 would be the similarity value. Similarities. Okay. And yes, we want top chunks. In the similarity doing slicing, and it's just return top chunks. Okay, it's done. Just writing test cases, sample chunks. No. So in the sample text we already created, yeah, I just added this word rag here. And if I hit a query sample rag, then this chunk and the chunk containing this should come up. So, okay, query equal to sample rag, and I have to use equal to ingestion.py. Just sample great importing ingestion, and then chunks retrieval, retrieved chunks equal to retrieval dot retrieve. And for index similarity in retrieved chunks, what does this return? This returns a list of top key chunks, and in this list we are printing chunk great. Nice. Oh, see, rag and sample. I think the whole implementation of this RAG framework is complete here. So it was just these three simple files. And yeah, with this, I we have completed. So yeah, with this, we have completed this implementation. And one thing that I think I skipped going in depth was how this was being calculated. This function, I just took auto accept on the collab. Mm, so we defined this vocabulary function for creating the vocabulary. We never called it. So when we are finally computing the TF-IDF score, we call the vocabulary function to create the vocabulary from all of the chunks and from all of the text. And then we create this IDF vector by calling the inverse document frequency calculator, which takes in the vocabulary. So pass this vocabulary there. And the term frequency vector. So for every chunk, the term frequency has to be calculated separately. So for every chunk in all of the chunks, we call the term frequency with the chunk and the vocabulary, because this takes these two things. And yeah, the TF-IDF vector, as I said before as well, is just a dot product of these two. And we append it to all the set of TF-IDF vectors and we done this. Cool. Okay, so that completes my implementation of a minimal functioning RAG, and how it will be submitted to the LLM is just that these very sentences will be added to the prompt along with a sentence like "you are a helpful coding assistant" or whatnot, and just read this and the query will be appended. This is what the user asked, and now give the answer. A lot of cases this is how it's implemented, and obviously there are many more layers that in the state of the art have been added on top of it. There are many more experimentations, but the core idea remains pretty much the same. And In a lot of cases, things like TF-IDF and BM25 are added to the more mainstream embedding models, transformer-based embedding models. And I'll in future videos try to implement different variations or versions of this same thing, which is closer to what is deployed in production. And lastly, thanks for watching so far, following along, and I hope it provided some value to you. I'll attach resources in the description related to TF-IDF and any other related readings. Thank you.